So this is a new song. This is called the MRI song. I had a bad experience with MRI machine. Any claustrophobics in here, this is for you. He said, son, this won't hurt one little bit. You'll be in and out in about 20 minutes. We're gonna strap you down, we're gonna slide you in. I'll see you on the other side, my friend. Just do your best to do the best you can. 2 minutes in and I begin to sweat. That's 2 minutes down, just 18 more to get. And I'll be danged and I'll be damned, I was gonna get inside this thing again. So I settled down and tried to settle in. I met Jesus in an MRI machine. When I couldn't move and I couldn't hardly breathe. I thought I was a badass, turns out I was deceived. I met Jesus in an MRI machine. 7 minutes in and my knees began to shake. My lips did quiver, my heart did palpitate. That was 7 down, 13 to go. They slide me out, I could hit the road and I could stay on this side of the pearly gates. I met Jesus in an MRI machine. When I couldn't move and I couldn't hardly breathe. I thought I was a badass, I was terribly deceived. I met Jesus in an MRI machine. And I could say religion stuff, but as soon as they slid me out, the gig was up. You know, I had a drink, I snuck a peek, I said some words that I shouldn't speak, and I found myself right back where I begun. Yeah, they slid me out, and I backslid right back to my wickedness again. But the truth of the matter is I'm still alive. If I'm ever in a bind again, take a call, my friend. See if he would bail me out one more time. And Jesus in an MRI machine, I wouldn't have when I couldn't move and I couldn't hardly breathe. I thought I was a badass, turns out I was deceived. I met Jesus in an MRI machine. Yeah, I thought I was a badass, I was greatly deceived. I met Jesus in an MRI machine. You know, Mother Teresa and even Gandhi too. Oh, they'd be proud of all the praying that I did do. I met Jesus in an MRI machine.
Welcome, EECS 16A. Woo! Good morning, everyone. I think it's the magic time.
Good morning.
Thank you, everybody that is participating. Much appreciated, all 460 of you. So now we're about down to half. We'd like to keep you having, participating throughout. So thank you, everybody that is showing up. Much, much, much appreciated. I also want to thank all those that put camera on, and really, again, like, I see your faces, it's nice. I got this big screen here, so it's nice to kind of see the feedback. Thanks, Anna, for doing like this with your head. You know, it's just like when I say something, I always look at your face, like, oh, was it okay? Yeah, okay, right. Let's.
I'm here, paying attention to everything.
Thank you.
And I look at their faces too to see if they're paying attention.
I know.
As you were talking. Yeah.
All 20 of them.
Good team. Good team.
All right, well, we got a lot of stuff going on today. Today, we're gonna do some interesting stuff. We're gonna talk about proofs. We're gonna talk about linear dependence. We're gonna talk about matrix transformations, all this really, really, I mean, to be honest, this is my favorite lecture. You know?
Don't start like that, Vicky.
Right? This is you know why?
We're traumatized by Tuesday.
Oh, that's right. Yeah, that's right. Yeah. Oh, I don't know what happened. I hope it doesn't happen again. But it is my favorite lecture. You know why? Because every lecture is my
Like
favorite.
this and like that.
It's just getting better, right? It's like this and like that. That's right. Yeah. All right, a few announcements. The quest is coming up. Quest is coming up, 9:14. I believe it's 8:30 or 8. Like, actually, take a look at the announcement.
Yeah, I think it's 8:45.
Yeah.
Dalia told us yesterday. Yeah, we should
think
pay
it's
attention,
We should, right?
but
Eh,
students should read
Yes,
the announcement.
they should. They should read. That's right. They should. Okay. Well, last time we talked. We continued the topics of vectors. We talked about matrix multiplication, and then matrix vector multiplication. We did like this and like that, and all that kind of good stuff. Matrix is amazing. I mean, everybody should tattoo like their favorite matrix on their hand or something like that. I mean, it really is. I mean, I know, think about what's your favorite matrix that you would like to tattoo. You don't have to tattoo, but like, just think about it. You know, some of them would like to put the identity matrix because, you know, they identify with it, but some other people would do something else. So we'll talk more about that. Zero matrix. Okay. All right. Well, and then we talked about span. What we're going to do today is we're going to go and give you some ideas about proofs, because the stuff that we say, you know, it doesn't come actually from nothing. You know, it actually comes from this thing in mathematics. Mathematics is so beautiful because there's really just this absolute truth when you can prove something. You know, it's just unbelievable. And so by making certain claims and going through certain steps, you can actually show that something is true. And once you've shown it, you can actually leverage that and then build on top of this. And it's just quite amazing. Then we're going to talk about linear dependence and matrix transformation at the end. So, okay, that sounds like a good plan, I think, right? That's going to be it's going to be interesting. So if you actually look at the proof, I mean, I would argue that you have to be very specific and not just, you know, say, oh, you know, this, and miracle happens, and then, you know, then that's that, right? Even though sometimes I would go about and say, oh, yeah, it starts from, but really there needs to be steps that you go through in order to do that. And there's different ways of proving things, but there's kind of a few concepts that I think are important to put in mind when you're going about proof. So first of all, when you want to prove something, we recommend that you kind of write out the statement with a direction that you're going to prove. So like if something, then something happens. You want to write that direction and see where it's going to go. Now, okay, how do you go about it? Well, people, you know, win awards for you know, coming out with proofs, right? So we're not going to get to those points. We're going to do a much simpler proof. But in those cases, what we recommend is maybe trying simple examples as opposed to going to, you know, for the general case, maybe just try a simple example to find a pattern. And that's kind of what we're going to do today. For example, if we're going to prove something for Rn, well, let's start, you know, proving something for R2 first, or R3, and then see if we can see some pattern about it. Now, what you want to use is you want to use something that you know. You use also definitions and other theorems in order to make your point. Then what you're going to do is manipulate both sides of the arguments. Okay, so you need to justify. So you have one side that you want to say something and the other side you want to say something, so you can manipulate them both such that you end up something in the middle that connects the beginning with the end. And then there's different type of proofs and tools to know. For example, a constructive proof where you actually give an example, or a proof by contradiction where you would say, you know what, let's say it's true. And then at the end, you get some contradiction, and obviously it's not true. So then you basically prove it by that. Okay, so what we're going to do today is we're going to show a few proofs. And I want to go back. We talk about Gaussian elimination. By now, you've done a lot of Gaussian elimination, but we said something. Some of the steps that we said, we really didn't actually show that these are true. Okay, now this is 16A. It's not, a math class, so we're not going to prove every single thing, but we still want to build you a mathematical, tools and mathematical thinking. So let's go back at the first. When we talked about Gaussian elimination, I said, there's this algorithm for solving a linear equation, and we're going to use these three basic operations that don't change the solution when you have a set of equations. Okay? And the first one we said is multiply an equation with a non-zero scalar. Okay. And, the example for that was, okay, well, 2x plus 3y equals 4. And we would argue that it has the same solution as 4x plus y. And the reason is because if I just multiply this by 2, and by 2, I would get, the other equation. So I multiply by a non-zero scalar. All right, and you believe me. I told you believe me. Okay, so now when I tell you to believe me, you probably should to some extent, but it's also better that we can actually prove this argument. So we're going to go now in a disciplined way and try to prove this argument. And you're going to see this all over and over again and again in this lecture today. Okay, so we can prove it for Rn, or for arbitrary number, so for n number of variables. But again, I just want to develop an intuition of how it works. So let's just prove it for n equal 2. And once we prove it for n equal 2, you would see how it immediately will translate into to an arbitrary n. Okay, are you ready? Woohoo! All right. So here's then our equation for R2. We say, you know what? What do we know? What do we know? Well, we know that AX plus BY equals C, right? Okay. Well, that's great. And the thing is, we know that this equation may have some solution that satisfies this. So, you know what? Let's just say, without loss of generality, that their solution is some x0 and some y0 that would satisfy this equation. Now, here, x is a variable, could have anything. Y is also a variable, it could have anything. But now we're saying, there is a solution for this. And the solution for this is a specific x0 and a specific y0. Now we leave it as a parameter. It could have been 1 or 2, but if we just use 1 and 2, then we'd have to prove it for 2 and 3, like all numbers. But instead, we just saying, okay, x0 and y0 are some solution for this set of equation. If you substitute this here, you would get C. All right? Okay. So in that case, ax0 plus by0 would indeed equal C. All right, so this is what we know. Now, what do we need to show? Well, we need to show that if we multiply by some non-zero scalar, then the solution doesn't change. Okay, so we're going to write that down. We're going to write down that show that beta, which is the non-zero scalar, times ax plus beta times by, that equals to beta c. So we just multiply both sides of this equation with this non-zero scalar, and we want to show, we don't know, that this equation has the same solution, x0 and y0, as the original equation. Okay, that's what we need to show. All right, so how do we go about it? Any ideas? divide by beta? Hold on. I mean, how do we know that it has the same solution? I mean, we know that x0 and y0 is solution for the first, but we want to show that it has the same solution. So basically, we want to know that x0 and y0 is also a solution for beta ax plus beta by, and that equals beta c. So how about we just substitute? Substitute x and y with x0 and y0 and see what happens, right? If we just substitute, then let's check if this is true. Okay, so let's check. We're going to substitute x0 and y0 for x and y, and we're just going to evaluate it. Okay, so this is the evaluation. And now we need to say, you know, is this equals that? Is this equal that? Well, let's just see. Well, what I can do now is take the beta, you know, as a common multiplier, and then effectively say, you know, beta equals ax0 times beta times ax0 plus beta y0. That is supposed to be beta c. Is that true? Well, let's see. We have defined, we know that this is true. We can plug that in here and then say, yeah, beta times c definitely equal to beta times c, because this equals c by definition, right? That's what we defined before. Okay, so that was just a simple step of logical steps. We went from here by picking a specific solution and then showing the argument and leveraging what we know in the solution to show that this is true. Okay. All right. But this is still not over. You know, it's not over because we did show that the solution for this, right, is the solution for this. So that didn't change the solution. But maybe by multiplying by beta, we introduced a new solution that is not satisfied by the first one. Now, this may sound to you stupid because it's a linear equation, and we all know that linear equation have, just one solution. But hold on. But we maybe want to prove that too. We want to prove that too, because that may not be necessarily true. So what we want to show is that by multiplying by beta, we show that, yeah, this has the same solution as this one. That's fine. But did we introduce a new solution now that not satisfied by that? How do we show that? Well, what we're going to do is just go in reverse. We're going to go and show that if there is a solution for this, it will also be a solution for this, right? We showed one direction. Now we're going to go backward. In order to go backward, we'll need to use the fact that beta is not equal 0, okay? Because we haven't used that fact yet, all right? Because if beta was equal 0, that would have been true. This, right? That would have been true, okay? Now we want to go back, okay? So this is not the only solution. So what we're going to do now is going to go the other way. And we're just going to use exactly the same trick and mechanism that we used in the first case. We said, this is what we know. We said beta ax plus beta by plus equals beta c. We say, well, it has some solution, x1 and y1. I don't know if it's the same as x0 and y0, but it's some solution that satisfies this, right? We know that there is one, so let's just say it's x1 and y1. Okay. All right. Well, what's then the next step? That means that if I substitute, I know that beta ax1 plus beta by1 equals beta c. And I need to show that this has the same solution as ax plus beta y equals c, right, for this equation. Okay, so y1 would also satisfy that. How do I do it? Substitution, right? Now, since beta is not equal 0, I'm just going to say, beta AX1 plus beta BY1 equals beta C. But now I can divide by beta, divide by beta, divide by beta, because beta is not 0. And I would get AX1 plus BY1 equals C. That means that this is also a solution, right? But hold on, that also means that, hey, it fits this pattern. Hence, X1 and Y1 are also solutions for AX plus BY equals C. And hence, solution of one implies the other and vice versa. Okay. Now, we didn't prove that beta is not equal 0 because that was actually the condition. Multiplying by an equation with a non-zero scalar changes, right? That non-zero scalar is an important thing, and that's what we need to prove. So yes, by definition, we said that beta is not equal 0. We don't need to prove it. That is actually defined. Okay, we're going to go through all of these type of proofs in the lecture. Hold on. I get it. Yeah. We're going to go through this, and you're going to see it more. Yes, Anna, go ahead.
Clarifying question. Not clear to many people why you had to prove twice. Both ways. So.
Okay, so why do I have to prove twice? Well, in the first case, I said, you know what, multiplying by beta doesn't change the solution. Okay, well, in that case, I would say, yeah. In this case, I showed that x0 and y0 is a solution for this. But maybe by multiplying by beta, I introduced a new solution. So yes, this one is the solution for this, but maybe there's another one. Maybe there's a solution for this one that is not satisfied by that. That I needed to show going the other way. The fact that I multiply by beta, maybe it introduced a new solution. I don't know, maybe. Because I did some operation. Well, what I did here is I showed that that isn't true. Any solution that has, that satisfies this, satisfies that, and vice versa. Okay, it's not just one directional. Does that make sense? All right, I'll let you digest that, and let's move to the second one. The second one is adding a scalar constant multiple of one equation to another. And if you remember, if we had a set of equations here, I said, you know what? What if I take equation 1 and multiply by 3 and add it to equation 2? I would argue that this set of equation has the same solution as this set of equation, right? That's the basics of Gaussian elimination. That's what we assume. And I'm not going to prove it. What I'm going to do is I'm going to give you an idea of how to prove it, the concept of the proof. So anybody has an idea how to go about proving it? What did we do with a scalar part, like multiplying by a scalar? The first thing is, you know what? Let's find an explicit solution, x1 and x2, right? That satisfy. And then we showed that that explicit solution satisfied the other one. Well, we can do exactly the same here. The concept of the proof, and you can look at the notes that we, that are provided on the class website, is to do the same. Look at an explicit solution, some x0 and some y0 that satisfy both equations, and then show that they satisfy this one. And in order to show that there is no solution for here that is not satisfying that, we'll go and do it backwards again. Okay, so exactly the same process that I did in the first case, you can do now in the second case. Does that make sense? So this is a methodology of proving these type of arguments. All right. So I'm happy that we're done and proving the Gaussian elimination because we are going to be using Gaussian elimination. So now we know that every step that we did in the Gaussian eliminations are true. And we prove that. So now we can leverage Gaussian elimination, for example, to prove other things. Okay. So again, build this house, a layered house, not of cards, because well, it could be cards, but like very strong cards. Okay, like made of steel, and connected very strongly. And let's go back and talk about span, and we're gonna prove a few things about span as well. If you remember, what is span? Well, span by definition is the span of the columns of a matrix A is the set of all vectors B such that AX equals B has a solution. And I said, you know what? Really, it's the set of all vectors that can be reached by all possible linear combination of the columns of A. So if you have some place that you want to reach, you take all of the vectors that are columns in A and try to find a linear combination of them to get to the point that you want to reach. And then we did this weird definition, but it's the same thing, just said in different words. If there exists an vector X such that AX equals B, then B is within the span of A, okay? If there is one that satisfies that, that means that B is in the span of that matrix, okay? That's saying exactly in the span of the column of that matrix, okay? So that was the definition. We just go back to what we covered before. And now we're going to do a proof that, and the proof that we want to do is, we argued again last time, is that the span of the vectors 1, 1, and 1 minus 1 was R2. And I used the, kind of like a hand waving with, what did I put? Like Marmite or like jelly, or, so it's basically you take a piece of bread, or toast, and then you put like, you take a knife and you put like this Jello, along a line, and then you smear it, right? And somebody said, what do you mean by smear and all that kind of stuff? And it's like, yeah, this is just colloquial. This is not really a proof. So let's just actually prove that this is indeed in R2. Okay, we want to prove that that is the case, that the span of these vectors is R2. Okay, so we're going to prove it. Are you ready? Okay, so again, in a proof, we know there is the part where we know, and then there's a part where we don't know, like we want to show, okay? Part that we know and the part that we want to show. So what do we know? Well, we know the definition of the span, okay? The definition of the span is the span of these two vectors is a set of vectors, okay, some vectors V, such that V is a linear combination of the first vector and the second vector, okay? Some linear combination of them, okay? That's what we know. And I'm gonna call that set S, okay? The set S is all the vectors that are linear combinations of these two, okay? This is just nice mathematical form that confuses people that are not familiar with this, but once you get used to this, you actually are very happy because it's a really accurate definition of what that actually means. V is a vector for which, okay, V, so this is a set of vectors V such that V is a linear combination of these two vectors, 1, 1 and 1 minus 1. Okay, that we know. Why? How do we know that? Well, because that's the definition of a span and it's defined. Okay, so what we need to show is that the span of these two vectors is R2, right? We know that the definition, right? These are linear combination, but we need to show that it actually is the entire R2. Okay, so what we're gonna do. Some ideas. Simplified unit vectors. Okay,
Make a matrix out of this.
We can make a matrix. Oh, hold on, before we make a matrix, how do we show that something is in R2? Oh, wait, somebody said take an arbitrary point in R2. Yeah, let's just take a vector that is in R2, and then let's show that it is within the span of these two vectors, right? So again, find an explicit solution, like give an explicit solution. Let's bring a vector from R2. Okay, so we're just going to say, we're going to pick a specific vector in R2, okay, that is parameterized by B1, B2. It's specific one. It's not, this is a specific one. It's B1, B2. These are numbers, okay, constant. And we know that these are in R2, okay? Okay, so we just pick them. And what we want to do is we want to show that B is within the set, that B can be represented by a linear combinations of these two vectors. Okay, that's what we want to show. Okay. So we pick one. We know it's in R2 now. All right. All right. So what we're going to do now is we need to solve effectively. Okay, so now we have the B, right? We have those Bs. And we need to show that alpha, some alpha times 1, 1 plus beta times 1 minus 1 will, we want to show that there is this alpha and beta. There is specific alphas and betas such that the linear combination of these will give me that. Okay, that's what we want to do. We want to find these specific alphas and betas, because once this is specific, then those alphas and betas become specific. Okay, this is a specific vector. Well, now there might be a specific alphas and betas that would then satisfy that. Okay, so effectively, we need to solve the following. Alpha times 1, 1 plus beta times 1 minus 1 should be equal to B1 and B2. And we need to find those alphas and betas. If we find them, then B1, B2 is within the span of those two vectors. If we don't, then it isn't. Okay, so let's find them. How do we find them? This is looks like a linear set of equations, but we can just write it in a nicer way, right? Let's look again. What is known in this problem? And what is unknown? What are known? Is this known?
Alpha, no, we don't know alpha.
Beta?
And we don't know beta either.
B1, B2?
Yes, we know them.
Yeah, we know them. Right, so these are unknown. These are known. And we know also that these are in R2. Okay. Okay. Well, what I can do is I can do this amazing thing. And you know what? Remember, this is the sum of the columns, a linear combination of columns of A. You know how we wrote the linear combination of columns of A? Remember that we said, oh, this is like 1, 1, 1 minus 1. But I can write it like alpha times beta. That's the same thing, right? That's exactly the same thing. All right, so let's just write it that way. Okay. And so 1, 1, 1 minus 1 times alpha beta equals B1, right? So now this has the form of AX equals Y, right? Like it's a linear set of equation that we need to solve. Okay. Okay, so we need to solve this. And we need to solve this. So how do we go about in solving this? Well, we proved Gaussian elimination. How about we find those alphas and betas using Gaussian elimination? Because that's already proven. Okay, so let's find those alphas and beta. And now I'm going to do it pretty quickly. So let's do it here. Okay, I'm going to write, 1, 1, 1 minus 1, and then B1, B2. And then what I'm going to do is I'm going to take this one and subtract from this one. And that will give me 1, 1, 0, and then minus 2. And then B1, and then B2 minus B1. Okay? Yes? All right, then I'm going to divide by minus 2. And dividing by -2, that leads to 1, 1, B1, and then 0, 1, and then B1 minus B2 instead of B2 minus 1 divided by 2. Okay, just because it's a minus, then I just flipped those two. Okay, and then you can keep going, and just for the sake of it, I already written this, and then I can just go and subtract this by this, and I get this. And that is in fact the solution. And the solution is that alpha equals B1 plus B2 over 2, beta equals B1 minus B2 over 2. And so effectively, I found an alpha and beta. If I found an alpha and beta, that means that B1 and B2 are in the span. Okay, so every B in R2 can be written as a linear combination of these two vectors. So B has to be in the set of S. And the beauty about it is that I can actually go and write now this equation. It says, you know, B1 plus B2 over 2 times that, plus B1 minus B2 over 2 times that equals B1, B2. Okay, QED. All right, that's beautiful, right? And what we leveraged here, well, we leverage a few things. First of all, a specific solution, and then some knowledge that Gaussian elimination is the right thing. It's a okay way that we proved already to solve a set of linear equations. Okay. So we effectively finished. This is the proof, right? If this has a linear combination of these two, that means that this is in the span. And these are the coefficients, specific coefficient of alpha and beta that you need to use. All right, any questions?
I have a question on why are we allowed to use Gaussian elimination to prove this operation?
Like this one? Yeah, because we used it, right? Because we proved that already. So anything that you already proved, or you know that it's a theorem that is being proved, then you can leverage it to prove a new theorem. That's the beauty of mathematics, right? You start, like if you know, I highly recommend, by the way, taking math classes, because it will just blow your mind. I mean, it's not easy, but basically they go through, you know, from the basic stuff, and then they just, you know, keep building and building and building, leveraging the theorems that is being proven from basic principles and proving newer and more complex theorems based on that. And it's just beautiful. Okay. All right, so this particular proof is called the constructive proof because I constructed a solution. I said, you know, that this is true. Well, here's the solution, therefore it's true. Okay, so this is a constructive proof as opposed to a counterexample. Okay.
Okay, I think Ryan has a question.
Yes, Ryan.
Before you go.
Yeah, I just have a quick question. So, like, how do we check that we're not zeroing out both vectors? Like, say both coefficients were 0, then that wouldn't work, right? Like in this circumstance, we didn't have that problem, right? But like, would there ever be a circumstance where both would be 0? And then they can't both be non-zero, both coefficients, alpha and beta, right?
Well, if alpha and beta would have been 0, that would have been not true. And so the assertion would have not been true. So you would have proven by contradiction that the theorem is wrong.
Okay, so it just automatically be wrong, right?
Yes, and that would be maybe a way to prove, let's say I would have, you know, in a different universe, in an alternate universe where this is actually wrong, and I wanted to prove it there, I would say, oh, let's assume it's true. Here's a solution. And then you get like 0 equals B. And then you would say, oh, this is not true, right? So that's a proof by contradiction in an alternate universe, like Marvel or something, like Marvel universe, right? That will be.
Yeah.
Anybody seen the movie, the new movie, Marvel movie? Raise your hand. I teach a sophomore seminar. 25% of that class already seen it. All right. Now I want to move and talk about linear dependence, okay? And I want you to recall that I had this matrix, 1, 1, -1, -1, and I call this A1 and A2, and we drew them, and basically they look the same. Just pointing in the opposite direction, that means that A2 equals minus A1. So in fact, in this case, we know that A1 and A2 are linearly dependent because I can write a function. I can write A1 equals minus A2, right? So they're linearly dependent. A1 defines A2, A2 defines A1, and so they're just basically the same equation, or the same set of solutions if we're going to solve a linear equation. Okay, so all right. So that was simple, but I want to define it in a more concise and accurate way. What is linear dependence? Okay. Now, you can ask yourself, is this electrical engineering, computer science? I mean, are you teaching us just math, Well, yes, we are. But hold on, because almost every single class that you would take in the department, you'll go over this again and show exactly like similar thing. You'll take, optimization, and you'll see this again. You'll take linear dynamic systems classes, that teaches you control. You'll see this again. All these definitions and all of these, because they're extremely useful for characterizing systems. Okay, when you want to characterize systems, you want to know maybe if there's linear dependency, and that's going to have implications about that system. Okay, so we're not teaching you this for nothing. And I think that is maybe the difference of taking a class, that we teach mathematics in electrical engineering, computer science, is because we definitely see the applications in mind, and we'll try to emphasize that at least. It's not just the pure theory behind it, even though that this is just beautiful theory, and it's just like I have tears in my eyes when I talk about it. Okay, here's the definition. Now, last time you've seen a grown man cry, now I'm just like, kind of wetting my eyes. We're going to define it in two different ways, and because those two different ways are useful, but they're exactly the same. A set of vectors, A1, A2, all the way to AN, so just n vectors. Yes, Adi. Do you have oh, no, you're still from the Marvell thing? Okay, all right. A set of these vectors are said to be linearly dependent if, what is E? Opposite. If there exists some set of coefficients that are scalars such that, what is that? Oof. That some vector in here, AI, is a linear combination of all the rest. That's what it says, okay? So I'm summing over all the values from 1 to n except I, and multiplying alpha j times aj vector, okay? That's what it says, okay? So some vector here, maybe, right here, let me just give you an example. Here's an example. What I'm saying here, that A2 is linear, like this set is linear dependent. For example, if A2 is some linear combination of other vectors that are not A2, and there exists some coefficients, alphas, that satisfy that. And the alphas in this particular case are very specific. Alpha 1 equals 3, alpha 5 equals -2, and alpha 7 equals 6. Okay. This is just a more general way of saying that. Okay, this is just a more general way. I'm summing over all alphas and and AJs that are just not I. Okay, that's exactly the same. 2 here doesn't appear here. There's no, you see, 2 doesn't appear. Now, if 2 would have appeared here, it would have been trivial because I would just set all the alphas to be 0, right? Except the one that is 2, right? So then that would be a trivial. So effectively, there's another way of saying that. What's the other way of saying this or that? Yes, Mihai.
I have a question about the example because I thought like A2 needed to be a combination of all the other. Oh, are we just setting the other alphas to 0? Is that what this
Yeah,
is?
so all the alphas could, the other alphas be 0. Yeah, yeah.
Oh, okay,
Absolutely.
okay.
Yeah, the other alphas could be 0. That's right. There just need to be some linear combination that is non-trivial. Okay, cool. All right, there's another way of saying this thing, and I'm gonna start this word with an S.
Span?
Ha! That's right. A2 is in with a span of what? Of these
The
vectors,
set
right?
of, yeah.
Yeah. So AI is in with a span of all of these, right? So I basically say that AI is in the span of all the AJs that are not J, where J is not equal I. Okay, that's another way of saying the same thing. So the definition, a set of vectors AI till AN are linearly dependent if there exist some coefficients. We don't know what the coefficient, but they exist. And if they exist, then and it's linearly independent, that means that AI is in the span of the AJs. That's what it means. And in this particular case, among all of these, I said, what, A2 is in the span of some other vectors, hence these are linearly dependent. Okay, that's the definition. Okay, so here's a question. Are these linearly independent? Are these vectors linearly independent?
I would say no.
Yufuma, you have a question?
Yeah, yeah, I have a quick question. So
Yep.
like if you have a set of vectors like n vectors, right? And you take one of the vectors out and then you say that and then you take another 2 vectors and you could like with those 2 vectors you can make linear combinations that could like equal that first vector. Then that influences the rest of the other vectors so that all of them are still does that influence like the rest of the other vectors that you didn't select out? Like you just need to select like a couple vectors and then automatically that they're all linearly dependent.
That is not necessarily the case, but what I said is that these are linearly dependent if I remove one of them, and then I can express that one with the rest. That's what I said.
Okay.
Okay,
So like
so
one of the vectors. Okay.
But I don't know if if I removed one now, I don't know if the rest will be able to represent,
Okay.
But what I'm saying is that these are considered linearly independent. If I remove one and I can represent the rest, I can present it by what's ever left. Yes, exactly.
Okay.
That's another definition.
Okay, thank you. I get it now.
Sure. William, let's.
So is the whole set linear dependent, or is it just like one vector?
The set of vectors are linearly dependent. The whole set. And I'm asking here if this whole set linearly dependent. Obviously, by the way, a subset of them are not linearly dependent, right? But the question is the whole set linearly dependent? What do you think?
Yes.
Yeah, I mean, I think so. But first of all, it's 3 vectors in R2, and we know that these span R2. And this is within the span, right? So, but we want to show that. Okay, so they are. So what we need to do is we need to do the definition. We need to show that, let's say, the third vector is a linear combination of these 2. If we show that, and we know the explicit combination, then we proved it, right? That these are linearly dependent. What's up? I'm gonna hold on that question for a second and let me just finish that, and then if we have another question, then follow up. Okay. So I want to show that this is the linear combination of these 2. Okay. Well, what do I do then? I'm going to write that linear set of equations. So I want to show that, 1, 1, 1, minus 1 times some coefficients, alpha and beta, equals 3, 1. Okay. If we find alpha and beta, then we solve the problem. Do you really recognize this, by the way? Because we actually solved it before for the general case, for arbitrary B1, B2. Now it's a specific B1, B2. The specific B1, B2 are 3 and 1. That was the same B1 and B2 as before. And remember that we already did, came up with an equation for these B1 and B2s. And so we know that B1 plus B2 over 2 times that, and that will give you this. So that's pretty obvious. I just need to substitute B1 with 3, B2 with a 1, and then I'm done. And then just show that it's true. And in fact, if I do substitute 3 plus 1 divided by, then I get 2 times 1, 1 plus 1 times 1 minus 1, and that equals 3, 1. Hence, linearly dependent. Yes, it's
Wait, Professor, so the entire goal of
Yes, student.
your entire goal of the theorem is like, as long as you can multiply the vectors by some coefficient and combine them, and if you get one of the vectors like in the set, that means it's linearly independent, or I mean linearly dependent.
Yes, but it's not a theorem. It's a definition. I defined. Right? It's not a theorem. I just said that the definition of linearly dependent is that if I take one vector and I can find a linear combination, then the set of vectors are linearly dependent. That's a definition, not a theorem.
And it can be any vectors. Like, and this one we were picking the third one, but how do you know to pick the third one? Like, can you just pick like any of?
Oh, I just asked you, do these satisfy that definition? Either yes or no. Right? I just asked. I just picked those, and I said, are these linearly dependent? I could pick random numbers. I'm just giving you an example. And then you go to the definition, and then you show that it's either yes or no. And in this case, we showed that these are yes.
Oh, okay.
Okay.
Cool. Thank you.
Sure. Yes, Mihai.
Then it's possible for like one of the vectors to be a linear combination of the rest, but not other ones. So
it
like,
could be. It could be. In this case, no, but in this particular case, that wasn't the case. But yeah, absolutely.
well,
Yeah.
I mean, like we picked the 3-1 vector, but if
it's possible that it's not a linear combination of a subset, yes. But that's not what I'm saying. I'm just saying linearly depends of this set of vectors means that you just take one of them and you can represent by the rest.
But my
Like
question
that-
is, if we picked a different vector, like if we picked the 1-1 vector and we try to express it as a linear combination of the other ones, it's possible that it couldn't be done.
No, that's not possible because
Oh, it's not possible.
I can pick any one of them.
And it should
Because
be possible
if this
if
is
it's a
represented
linear.
by these two, that means that I can actually take this one and represent by these two.
Okay.
And I can show that too. And if I take this one, it will present by these two. If these are linearly independent, by definition, you pick one. It doesn't matter which one you pick. It can be
Okay.
represented by the rest. I'll take one more question. Somebody that haven't spoken before. I think Yuja?
Hi, Miki. So basically, by showing that they are linear dependent, are you saying that the vector 3, 1 is in the span of the matrix 1, 1, and 1, -1? And graphically, are you showing that for the vector 3, 1 on the graph, we can use the vector 1, 1 and 1, -1 to get to this point of 3, 1? Is that
You couldn't say that with, I couldn't have said that with better description. It's absolutely correct.
Okay, thank you. Mhm.
Thank you. All right, I want to move on for the sake of it. Simith, if you want, just write on the chat if you don't mind. Okay, so yes, these are linearly dependent. Okay, so when I look at these, I can actually say another thing. Okay, I can say another thing. The other thing I can say is, you know what? If I take 2 times the first one plus 1 times the second one minus 3 minus the third one, that would be equal 0, right? I can say that. Why is that true? Because this equals to 3, 1. And then if I subtract that one, that will equal 0. Okay? Saying that these two equal that is the same thing as saying that these two minus that would equal 0, right? Same thing. Okay, so I'm just going to define linear dependence in a slightly different way. I'm going to say definition 2, a set of vectors a1, a2, all the way to an are linearly dependent if there is a set of coefficient, if there exists a set of coefficients alphas, such that the sum of all the the linear combination of all these vectors has a solution 0. That's exactly the same as saying, take n minus 1 of them, represent by the other one, represent the other one, because I can just take the sum of them and then subtract. Okay, so there is some alpha coefficient such that if I multiply those alphas, will be equal 0. Now, somebody might say, let's just set all these alpha zeros, right? Well, except it's linearly dependent as long as, not all of them are zeros. Does that make sense? So that's just a different way of saying exactly the same thing. Okay, so if there is some alphas such that you multiply each of these alphas by these A's, vectors A's, and then sum it all together and you get 0, these are linearly dependent. Okay, if I show that, then that's the same thing as showing that one of them is in the span of the rest of them. It's exactly the same. I have not changed anything here. Okay. And then if I want to define the converse, like what is linearly independent, well, any set of vectors that are not linearly dependent are linearly independent. Okay, that's again a definition. So if I give you a set of vectors and you cannot find a linear combination that leads to 0, well, they are linearly independent. If you find, they're linearly dependent. Okay, that's it. All right, so these are the definitions. And now the question is, are these vectors linearly dependent? Obviously, it's the same thing that I did before. Before I had like a 3 and 1, now I put a pi and square root of 2. It doesn't matter. These live in R2. These span R2. So yes, these span R2. This lives in R2. This is when the span of these. Yes, linearly dependent. Okay. All right. Now I'm going to show a theorem.
Lots of questions, Vicky.
And I will take one. Yes. Stay down.
So if two vectors, or like the first two vectors are like they define R squared, the third vector, if it's in the span, is also, I'm not R squared, it's in R2. But if the third vector wasn't in the span of like the first two vectors, then would that define R3?
Hold on. What you're saying is, if these define R2, this has to be R2 because it has only 2 numbers.
Yeah.
So it cannot define R3.
Oh yeah, okay, never mind. Yeah, that's right.
Right. These are all vectors in R2. These define the entire R2. Okay. Any linear combination of them will span the entire R2. By the way, that's also true for these two, and that's also true for these. Okay, and you can show that as well. Yes, Aman.
Two questions. First of all, can a set of vectors have vectors of different dimensions? So like one with like a size of 2 and one with a size of like 5?
Well, then it would be not be a vector, a set of vectors of Rn. It will be a set of vectors with different dimensions. But
Okay. Okay.
but it
And
doesn't.
also,
But you cannot show. I mean, you cannot add them together. You cannot do much with them. So I can see in some alternate universe somebody might want to use that to prove or say something, but not right now.
okay. And also assuming all the vectors are of the same size, like
Well,
every set.
linearly, look, it's just the definition. It's a definition. Linearly dependent. It's only talks about
Okay.
vectors with the same size.
So every set of vectors would either be linearly independent or dependent, right?
A set of vectors of size Rn, Rn, and I'm taking M of them, will be linearly dependent if the definition applies. Okay, that was the definition. I said we're taking these vectors and their size that, and there's M of them and so on and so forth. It's in the definition. If you do something else, then it's not within the definition. Then you might need to prove.
I was just saying for that set of vectors, it's either linearly dependent or linearly independent, right?
That's
it can't be
right,
like
yes.
in a middle ground or something. Okay, thank you.
Yep. And Adam, I will take one more question then, just for the sake of time. Yes.
So if we have a set of vectors that spans Rn, can we show that if we add to that set any vector from Rn, that set is now going to become linearly dependent?
I think we showed that. Because we have now an equation. We can find an alpha and beta to reach any arbitrary B1 and B2. And then if you add another vector, then that's could be your B1 and B2. Right?
Okay.
Right. So effectively, we kind of show that. We showed it specifically for 1, -1, 1, 1, but you can show it now arbitrarily. Yeah. Okay. Because you can find basically an equation that does that. Yeah, that's a good point. Okay. Here's a theorem. If the columns of the matrix A are linearly dependent, okay, then AX equals B does not have a unique solution. That means that it has multiple solutions. Okay, that's a theorem. Now, why is that useful? Well, remember the tomography case? We had some A, right? When we made only 4 measurements, and we found that there was no unique solution. Well, we could have then checked if those vectors in that matrix A were linearly dependent, and then we wouldn't have to go through all those steps. Okay, so the theorem says if the columns of the matrix A are linearly dependent, then AX equals B does not have a unique solution, it has multiple. Okay, that's what it says. And we're going to prove this theorem, and it's extremely useful theorem. Okay, extremely useful because it tells you something about the system. Now you have a test. You have a test that you can check. Do I have many solutions or I don't? Okay, I'm not testing, by the way, if there's no solution. Obviously, no solution, then this is not true, right? We're looking at the case if A is linearly dependent, then this does not have a unique solution. All right. Here's the proof. Let's start. Consider the, no, I'm just kidding. Let's just prove it for, let's just prove it for R3, okay? And you can see that you can prove it for arbitrary Rs, okay? Yeah. All right, let's prove this for R equals 3. Again, what we know and what we don't know. Hey, can you hold on for the rest, or like you're asking a clarification question about what the theorem is? Hike.
It was just a clarification question.
Okay.
But no, I can wait till the end because it doesn't really matter.
Okay, thanks. Okay, we're gonna prove for R equals 3, okay? So what we know, again, proof is what we know, and then we need to show. So what we know is that we know that the columns are linearly independent, right? That's the definition. We said if the columns of matrix A are linearly independent, okay? Now, we need to show that there is no unique solution. Okay? Well, I think it's enough if we show that there is 2 solutions, or at least more than one, right? That's enough. And then we're done. Okay? So we need to show that there is more than one solution. Okay, so what are we going to do? How do we start? Wait, hold on. Somebody says, yeah, so these are, again, by definition, we said that the columns of A are linearly dependent. We know that. That's the theorem. If it is, then there is no unique solution. Okay, so we know that they're linearly dependent. So how do we show that there is more than one solution?
We can show that by contradiction. We can assume that it has only one solution and then show that it has more than one solution.
Oh, yeah. Well, I mean, yes, it's kind of by contradiction, but we can also be specific and just find another solution, right? Let's start with a solution, right? So yes, absolutely. There's different ways that you can show this. I agree. Yeah. So the concept that we're going to do is we're going to pick some specific solution, X star, and just show that there's another one.
Professor?
Yes.
Sorry, it says we know that the columns are linearly independent. So why would we try to like find another solution?
Oh, wait, hold on. That's a typo. Thank you. That is stupid. Thank you for that.
I made this mistake a couple of minutes ago.
Sorry about that. Yes, the columns are linearly, you know what? Let me just fix it in the slides now. Okay. So we're going to pick a specific solution, okay? And the specific solution then says, you know what? Let A X star equals B. Okay, we know that X star is a solution, so A X star equals B. And we want to show that there's another one. What is A? Well, A is, you know, has column vectors, right? So A1, A2, and A3. All right. So now we need to use the fact that these are linearly dependent. How do we use them? Well, I'm going to use definition 2, okay? So from definition 2, because they're linearly dependent, there exist some alphas such that A1 times A1, alpha 1 times A1 plus alpha 2 times A2 plus alpha 3 times A3 equals 0. How do I know that this is true? Well, it says linearly dependent. That's the definition. So we're going to use this. Okay. All right, we're using this. And now I can just write that as a set of equations, right? Like I can write that as the matrix equation, right? I can just go and specifically write that. So I would say, yes, the matrix A1, A2, A3 multiplied by the vector alpha 1, alpha 2, alpha 3 equals to 0. That's the same thing, saying that. And this is the vector alpha. Those are the specific ones such that this linear combination would be equal 0, just by definition. Okay, all right. Anybody now has an idea to find another solution? We know that this is a solution. We know that multiplying this by this will always be equal 0. No, this is not 0. Alpha 1 and alpha 2, alpha 3 are not 0.
What if we add a constant?
To what?
To the alphas.
Hold on. Before you add a constant to the alphas, well, that's not necessarily going to be true. If you add a constant to the alphas, well, this is not going to be true.
Or if we multiply by a constant, would that still not do anything?
If you multiply a constant, well, then it'd still be true of 0. But we want to find a solution for ax equals b that's different than x star. X star is a solution for ax equal b. A times alpha equals 0, not a solution. It's not equal b, it's equal 0. We want to find some, let's say, x dagger, such that ax dagger equals b. That is not, oh, somebody said that, x star plus alpha. Let's see. Let's say that, let's set x dagger to be equal x star plus alpha. That's a different value. Let's see if this is a solution. Okay. Well, ax dagger equals a times x star plus alpha, the vector, by definition. Okay, but now we can take a times x star. What is a times x star?
We said it's 0, I think.
No, a times x star by definition is
B.
b. And what is a times alpha?
0.
We said it's 0.
0. So the whole thing equals
B.
b. So it's another solution. Right? So ax star plus a times alpha equals b plus 0. Hence, a dagger is another solution, and it's not unique. All right, QED. Or as somebody would say, KQED. Okay, so X dagger is another solution. So we proved this. Basically, we found another solution. Okay, in the last 10 minutes, yeah, X star, by the way, was just an arbitrary solution, right? Like I just said, it's a solution. I know it is a solution. Well, let's find a different one then. That is non-trivial, right? Like not adding to it 0. We added alphas, that alphas are not zeros, right? So there's another solution. I can go through this step again. That's important, actually. So let's do the whole thing, and I'm just going to show you again. So we said the columns are linearly independent, and we need to show that there is more than one solution. So what we said, you know what? Let X be a single solution. X star be a single solution. That solution means that AX star equals B. That's a definition. Okay, we just decided, okay, if there is one solution, this is the solution. Okay, now we need to find another one that is different than X star. Okay, that means that there's multiple solutions. And so how do we do that? Well, we said, you know what, from linear dependence, we know that A1 times, we know that this sum equals 0. And so I know that A times some alphas that are alphas not equal 0 equals 0. How do I know that? Well, that's the definition of linearly dependent. Okay, so there is an alpha that's not 0, a vector alpha that's not 0, that A times alpha equals 0. How do we know that there is a solution? Well, because we only said here that there's no unique solution. So we're assuming that there's one at least. Okay, that's again by definition. We said AX equal B does not have a unique solution. So there's one, but we said that they had at least more than one. Okay, so there has to be a solution. So I'm just saying X star is that solution. Okay. If there's zero solution, well, it doesn't hold. Then it doesn't mean anything. You know, that's not what we're talking about. Well, then that's not the case, right? If there's zero solution, then it's a you know, do your ear things, like, you know, put your hands on your ears. Yeah, that's if there's just like this. We're not talking about this case. We're talking about if there is a solution, it's more than one. Okay, I warned you. Okay, so then what we did is we said, you know what? This is a solution. Let's add it some numbers. And we showed that this is a new vector. And we showed that this new vector is also a solution. Hence, there's more than one. Okay, that's it. All right, I'm going to move on. And if you want to, you can go office hours and ask more questions about that, or watch it again. But just for the sake of time, I just want to move and talk a little bit about matrix transformations. And I don't know if you've seen this, but this is funny in so many different ways. And hopefully I'll explain why this is funny. Okay, this is a matrix times a vector, and this is on the side. Okay, so matrices, when we multiply, we looked at them as linear combination of the columns, we looked at them in the row, but we can also think of them as operators. Again, it's just a different way of thinking about stuff. So when I say A times X equals B, I'm saying, you know what? A operates on X and spits out B. So it does something to X and X turns into B. Okay, that's from a conceptual point of view. And if you think about a system, you have some inputs coming in and there's outputs coming out. You can think of A as performing an operator or transforming that vector into something else. Okay, so here's an example. Let's look at 1, 0, 0, minus 1. Almost an identity matrix, except that it has a minus 1 over here. And then I'm going to apply it to an arbitrary vector x1 and x2. If I apply it, I will get x1 and minus x2. Okay, let's draw what it does. Let's just pick an arbitrary x1. This is just arbitrary. What would happen to it after we apply a on it? Well, if the x1 coordinate doesn't change, the x2 coordinate will flip, become negative. Okay, so we'll move to here. All right. Now think about it, what that kind of operation means.
I've been working on this reflection.
Someone's reflection.
Reflection.
There's a reflection of the man's face.
The reflection.
There's a reflection.
Zoom in on the mirror. You can see a reflection.
So what is this? Zoom? No, it's a reflection, right? It's a reflection operator. This is a reflection matrix. The matrix reflects about the x-axis. Okay, that's what it does. So I can take now arbitrary vector, like another arbitrary, the blue one, and after performing the operation, it will come over here, be reflected. And if I take a red one and put it here, it will be reflected. And then what if I take a mountain that these are pointing to? We'll think of the x-axis as a lake, maybe in Grand Teton Park, and then it would be reflected. Okay, that's what it does. Basically, every point on here will be, after being applied the operation a times those points, then it would be reflected. Okay, so this is a type of a reflection matrix about the x-axis. I mean, I can find other reflection matrices about some other axes, but I'm not going to do it now. I'm just going to show you another matrix. How about this one? This is a matrix times some arbitrary x will give me that. Oh, so many cosines and sines and all that kind of stuff. And I have no idea what is going on. Let's try to simplify and figure out what this matrix does. So I'm just going to take a simple solution, a simple vector. I'm just going to pick 1 and 0. Okay, this vector. And then I'm going to apply that to this vector. And the result is cosine and sine theta. Cosine theta and sine theta. Okay, well, what does this vector does then? It rotates my input vector by theta degrees counterclockwise. That's what it does. This is a rotation matrix. And now if I apply this on this vector, what would happen? It will rotate again by another theta. And if I apply it again, it will rotate again by another theta. And if I apply it again, it will rotate again by theta. So it basically rotates the entire space by theta degrees. Gorgeous. Now you think it's funny? Because it's kind of rotated, you know. The A1 is like also rotated. See what I'm saying? Like instead of, yeah. Did you get the point? It's funny. It's supposed to be fun. All right. So I'm just going to finish with this, and then next time we're going to do some examples of some other things. I would say that when you look at linear transformation of vectors, okay, linear transformation, so a matrix transforms a vector, but let me argue that it's also a linear transformation. Okay, so here's the definition of linear transformation without matrices at all. If you have a function of a times x, you scale your vector, then if it's a linear transformation, it should be homogeneous. That means that I could first compute the function on x and then scale it. So these can be reversed. Take x, scale it, put it through the function is the same thing as take x, put it through the function, and then scale it. Homogeneity. And the other property is superposition. Take x, add to it a y vector, put it through a function. It's the same as taking x first, putting through a function, then take y second, put it through the function, and then add the result. It doesn't matter if you add before or you add after. That is superposition. If that is true, this is a linear transformation of the vector of a vector. Okay. So let me argue that matrix vector multiplication satisfy linear transformation. And you can easily show that if you take a times alpha times x, that would be equal to a alpha times ax, right? So first compute this and then scale, or first scale and then compute, it will be the same. And then I can also say that a times x plus y equals a times x plus a times y. First compute this, then compute that, and then add them together is the same as first adding x and y and then computing that. Do you believe me? Well, if you don't, you can prove this by explicitly writing the elements of those matrices, and then, you know, just showing that if you first add these two and you multiply all this A11, A12, all that stuff, you can actually decompose it by massaging two sides of an equation to be the same. And with that, we will see you next week. So next time, we're going to talk about transition matrix and stuff like that. It's pretty cool. Good stuff.
Thank
Have a nice day.
Thank you. Bye.
Bye-bye.
Thank you. Bye-bye. Bye, everyone.
Thank you.
Thank you.